That was actually a nice experience, but it's good to know that things needs to be improved in every place, and that specifically addressed if you start working in a situation where you help and assist lives of people who are unfortunately cannot do all the things that they would love to do on a daily basis. So if it is possible to improve the quality of life, then we're doing a good job. If we cannot do that, then we have to work harder in order to get this better. I was asked when we were preparing the meeting to talk in general about electrical stimulation and how it works. And does that sound okay? Perfect. So what I did is I prepared a short presentation which includes several aspects. Some of those are aspects that are dealing with functions that are important for the life, and then I will concentrate on control of movement for upper extremities and lower extremities. That's what I want to do. Sometimes what happens is people include in their presentations the best success in the motor control, and this best success in motor control is definitely a heart pacemaker and cardioverter. So there are millions produced on a daily basis and distributed, and people have normal lives. So that is also functional electrical stimulation. It has the same principle as other systems, but I won't be talking at all about that. So we're talking about problems that can arise because of a central nervous system. One approach of how you can start dealing with this is obviously to start activating and controlling the center of all information that exists, and that is our brain. So there are two possible techniques that can be used for that. One is to use surface electrodes, put them over the scalp, and then activate them with some DC or low AC currents, and then try to do something which no one really understands what they're doing. Or you can do this in a reasonably invasive way, or unreasonably invasive way. I think it's reasonable. And I'll run just a movie once more. So with two stimulators bilaterally, what you can do with implantable electrodes that are positioned at the right position, what you can do, you can activate brain cells. And if you activate these brain cells, then you can treat various disorders. And this technique was invented in France. And when it was invented in France, then what actually happened, which is nice and good. Can you see all the screen because of me? Yes. Okay, thank you. So what happened, I can sit down if that's easier.
You can move also if you want.
But then I cannot press the computer.
Mm-hmm.
Anyway, so this can treat problems that are typical for Parkinsonian disease. But there are other applications which are very important. So you can treat depression. You can control, as it's written here, obsessive compulsive disorders. And there are some controversial issues about that. Because what may happen is if you just put the electrodes part of a millimeter deeper down, you can actually change completely how the human behaves. And that's the question, who is the one to make a decision? Can I prevent your obsessive compulsive behavior? Is that okay or not? So that's not something that anyone can do. So there are some, I would say, slow down things. But in general, this technique is improving, the stimulators are getting better, the electrodes are improved, and the positioning is very fine. The next in line, and what you can activate in the body, the central nervous system, is obviously systems that are below that, and that's spinal cord. Spinal cord in animals is actually a center for movement. It can be called a brain for movement. There are central pattern generators located there. There are many other functions. In humans, these functions are overtaken by the brain, and there's only a portion of that that is really controlled from the spinal cord. But one part of that is definitely that you can position electrodes, which will be epidural, and that is not a very invasive procedure. And with this procedure, what you can do, you can actually, by selecting one of up to 16 channels that are positioned on both sides of the spinal cord, you can control pain to some level, but you can control many other things. There are methods these days, and one of interesting approaches that is actually being presented today in Vienna. There's a meeting in Vienna today, and it was yesterday as well, where they're talking about using surface electrical stimulation, which is positioned on the surface of the back, and by that activating the circuits in the spinal cord, and by that activating legs to move. This work is done by Winfried Meyer and his group and Dimitrievich and other, and it's an interesting idea, and how well it will work we'll see in the future, but definitely there is some future also in activating the circuits which are within the spinal cord. Now, this is related to some of the functions that are important for control of movement, but there are other extremely important elements. One is if there is a spinal cord injury and it is in the high spinal cord, C2, C3 levels, then there is a basic problem that the person cannot breathe. And if someone cannot breathe, obviously, then there's no life. So you can have artificial lungs, but the alternative to this is an extremely well-developed technology, which is a commercial product by the company Avery, maybe some other companies as well, I know only this one. And what you can do, you can bilaterally position two electrodes over phrenic nerves. And if you stimulate these phrenic nerves with rhythm, which is every 3-4 seconds, so there's a burst of pulses going to the nerve, that will activate the diaphragm, and by that you have the breathing activated and the person can live a reasonably normal life. This device works very well, but the injury, which is so high at the level C2, C3, is extremely complicated, and there are many other problems that are there. So in many cases, although that works very well, this is not really making a big difference in the life. There are other important in the list of functions that are there. Controlling the bowel and bowel are some of the major issues that people with spinal cord injury have to deal with. And the system that was developed originally by Brindley in UK was actually opening for the whole series of similar devices. And what you see here is an implantable commercial system that you position on the roots of a spinal cord at the lumbar zone and the sacral zone, and there are 3 of these electrodes that go there. So what you can do if you activate the stimulator, and this stimulator is being activated by pressing the button, you send a series of pulses. These pulses are actually activating the bladder. The bladder is getting emptied. There is the other device which is also being under development, which controls that the bladder is not leaking. So here we're looking for emptying the bladder. That's the system that I'm showing. But at the same time, you can have a device which prevents leaking. So if you have a combination of those, so you can keep urine in the bladder for every time. That's extremely important, because if you have the urine for too long time in the bladder, it will go reflux and goes to the kidneys, and the kidneys can be a killer in a situation like that. So this is an extremely important device, an important technique, which is replacing catheterization. So that is on the way, and electrical stimulation can deal with this. Obviously, I'm not going to show here, but there are devices that are being developed for control of bowel. Not working very well at this time, but they will be improved. I'll move to the second part, which is the topic that I actually wanted to talk mostly. That is control of movement. And this is a very famous professor, Jean-Benjamin Duchenne, and all the work is associated at the beginning is with Duchenne. So what he did many years ago, he was looking into patients, some of the psychiatric cases, and he had a stimulator, a big machine, which was on the side, and he had electrodes that you can see that he can put on the face. And if you look into this, he created an electrical smile. So if you look into Wikipedia or even something else with Duchenne, you can find that he could create easily up to 24 different expressions on the face, just by touching different places on the face. What he was doing there, activating facial muscles and activating some of the central net pathways, and by that he could create and change. Obviously, this is not only how the face looks like, but that actually activates some other functions that are related to that. So, based on that work and many other things, the idea started coming better, and this is, at least through my eyes, the very first presentation of an idea of what a neural prosthesis based on functional electrical stimulation should do. One of the important persons in the development of that is J.B. Reswick. J is for James, or Jim Reswick. So Jim Reswick was a very unique engineer in the United States, who was at Case Western Reserve Institute at that time, and then he was in California for some time. And he was fantastic in the following sense. He's the one who built the first Rancho Golden Arm, which was a robotic system which could assist people who cannot do anything. He was the one who developed the first implantable system. He actually implanted in himself in 1970 a set of electrodes into his shoulder, traveled from the United States to the place of Dubrovnik at that time Yugoslavia and Croatia, and he demonstrated how he controlled artificial extremities by implantable electrodes. So a very unique person with all kind of knowledge, and he was the one who actually created the team. And this team with Lois Vodovnik mostly and some other, they said, okay, if we have some circuits that are broken, then these circuits that are broken, they cannot be repaired because we don't have methods how to repair these nerves in the central nervous system. You can repair a nerve in a peripheral nervous system, but you cannot repair a nerve in a central nervous system yet. I'm sure that they will come, but yet it cannot. Anyway, what he said, okay, if we cannot repair it, we will make a bypass. So what I'm going to do, I'm going to pick up signals from the brain, or from spinal cord, or from wherever, and I will bring these signals all the way to the periphery, and I will control many muscles in a way which is very similar or almost identical like the nature will do, and based on that I will create functional movements. So this was the work which was presented at the meeting, which was a series of meetings. There was a second one in a series of 10. Some of these ideas are actually taking place these days. And here is Grégoire Courtin, and he is linked to Lausanne and to Geneva. And he has some excellent ideas that are combining many approaches that are taken into account these days. First of all, he's considering that within the spinal cord there is a central pedal generator. Central pedal generator meaning that there is a mechanism which will turn left, right, on, off, so a switching generator at various levels. So if you stimulate spinal cord by activating some parts, you can actually activate the different muscles that are operating left leg, right leg, flexion, extension. And at the same time, what you can do, you can pick up these signals from most of the work that he did, or I would say all the work that he did, is in rats. Rat is not a very good animal. No, it's actually a good animal for the research that you're doing, but not a good model. For two reasons. First, a rat will survive everything. The recovery of rat is absolutely immense and uncomparable to anything else. So if you have something that works in rats, it doesn't mean that it will work in any other animal, not to mention a human. The second thing in rats is obviously rat is a quadrupedal walker, so not the biped pedal. And animals who are walking on four legs, they have a completely different mechanism because they have a different balance and everything else. So that's not a very good model for that. But nevertheless, that's a good experimental animal to do stuff and see what you can do. And what they did in a joint work with quite a few other people, they developed a technology that you can combine electrical stimulation, which will stimulate with frequencies of 5 hertz, 10 hertz, 15 hertz, various frequencies, various amplitudes, the spinal cord with electrodes that go into the spinal cord. They can stimulate also something on the periphery, and by that they can actually get rats suspended in a specific robotic system to walk stairs, and behave reasonably normal after a period of that. So this is a very valuable approach, and these days they're starting to use this in humans. So in humans, what you can do, you can implant a system like that. What this movie presented is actually that there is an expectation that that will contribute to the recovery or repair of the nervous system. But what's wrong with this? Okay, it doesn't want to run. But I don't think so. The central nervous system, not that I don't think so, many other agree with me. Central nervous system has a mechanism which is defending reintegration of anything that you put in. The work that was done many years ago at the University of Miami and many other places demonstrated that you can physically bring a nerve into the spinal cord and that it will cross the lesion. So that works, but functionally you don't get anything. So the integration of artificial things in the central nervous system doesn't work. What came out of most of these things and research that started quite a few years ago is that functional electrical stimulation can actually have a specific modality which is called functional electrical therapy. What's the difference between functional electrical stimulation and therapy? You have devices that have an orthotic effect, and you have devices that have a therapeutic effect. An orthotic effect is an effect where you immediately get the function, but there is actually very little or no carryover. So a heart pacemaker is a typical orthotic device. So it gives the pulse and the heart contracts. But if you turn the pacemaker off, then there is no carryover effect of that. Similar as with some other devices which I didn't mention at all, like a cochlear prosthesis and another. So another possibility is that if you're using electrical stimulation because you're activating some of the circuits, there is a very specific behavior of the brain and spinal cord, and there are changes that are taking place in the spinal cord and brain, and because of that, there is a therapeutic effect because there is a carryover effect which may be very effective for the person. Obviously, you have to select a technology and technique that will assist that and help that, because it may also have negative effects if you don't use it in an appropriate way. So what you actually do with this is that you consider that electrical stimulation can work as a therapist that will affect first and change the cortical excitability and spinal cord excitability, and then as a result of the changes of the cortical excitability and other, it will actually affect and produce something which is called plasticity, and plasticity means that things will change, modify as they were when you're activating them. That has been demonstrated, and I use this slide because I like it very much. It's a good presentation. This is a work by Nudo, published in 1997, 20 years ago. And what you see here in a monkey, what they did, they intentionally injured the brain, but with a needle running into the middle and just the zone. And what you see here, they specifically injured the zone where the hand is controlled from, and the black, you see the circle, and that's the zone which was affected. So they injured the part of the brain which is controlling hand. And then they had two groups. One was monkeys that were not treated, and the second one were monkeys that were treated. Treated means they were part of a process of learning how to do things, which was motivated by food and drinks. So you don't give monkeys to drink, and then you give them some orange juice, which they prefer. And then when you give them, they are very keen to actually do what you say to do. Not an easy experiment, but done. So if you look into rehabilitation, where there was no rehabilitation lesion, you can see that at the regional lesion, there is a change of the size of the zone which is related to hand, and there is no recovery of that. But if you include an exercise program, then you can see a reorganization. You see the large black zone on that, and this large black zone on that, and you see the lesion still now is taking part of it. But if you now compare these two images, or three images, then you can see that actually it's now control of hand is taking a larger portion of the brain, which means that it took over some circuits that were controlling something else. There's some very interesting research studies that were done, for example, in people who play violin, and if you look at their brain, left side and right side, you will see that the region which is related to finger movement of the left hand, which is the right side, is enlarged. And the region in the brain which is related to control over arm manipulation, so shoulder and arm, because you're playing a violin, is enlarged. So by training, you can actually change the organization of your brain. This means that if you don't use your brain, you're definitely changing the organization, and you belong to the category of people who don't know what they do and cannot really move. So activating the brain is important, and activating the brain you can do in various ways. The best way to do that is actually to provide an input. An input is a sensory input. So afferent fibers coming to the brain and spinal cord. They're actually doing a great job. And how you can do that? We have sensation in our fingers. So if I start touching my fingers, this sensation goes into my brain. So the complete circuitry which goes up is activated. If I move my hands up and down into dorsal, so that again brings a signal from proprioceptors, from muscle spindles, and from Golgi tendon organs. So I can do that, and I can do that by having a therapist moving my arm or leg, which would be a passive movement, or I can ask a person, do it yourself, maximize your effort, which will be an active movement. I can do this passive because a therapist is not necessarily human. This can be a robot, which is replacing a therapist in this specific job. And finally, the third way how you can do it is to use the electrical stimulation. But the electrical stimulation has actually two effects. it does activate immediately circuits, because electrical activity simply creates action potentials on the sensory nerves. But in the same time, what it does, it activates the muscle to operate, so there's a combined function. So it's actually a dual operation when you use electrical stimulation compared to some other devices. So that's not electrical stimulation, but is important for what I'm talking. An approach for rehabilitation of people with physical disability, motor disability, is to use robots. Robots for upper extremity typically are devices which are assisting a person to control the shoulder and elbow. Some with wrist, but there are only very few which do that, and there are very few, not to go far. The best work, or the largest amount of work, was put into the device which was developed at MIT in Boston by Neville Hogan originally, but then afterwards overtaken by Krebs, an excellent Brazilian researcher. And Hugo Krebs actually developed a very nice technique how you can deal with these elements. And what they demonstrated, that if you have individuals who are being trained, and this MIT and other robots which are similar, what they do, they have a passive mode, they have an active mode. In the active mode, what they do, if the person cannot move the arm, the robot will move the arm. If a person has some abilities, then the robot will not do it. And it can work in an intermediate state, so if there is some power but not sufficient, it will assist the movement. So what was demonstrated, if you look into these graphs on the right side, the task was to draw a circle. And when you have to draw a circle, after 6 weeks of therapy, you see this very funny shape, which has not very much to do with the circle. And after 11 weeks, you see something which is more or less a circular shape. The right graphs are showing the velocity. A typical movement is characterized by a bell-shaped profile. So you start with the velocity 0, you go to the maximum velocity, and you end up with 0 velocity. So it's a bell-shaped profile, and it's a smooth curve. So healthy movements are characterized with bell-shaped, smooth curves. So if you look at the pattern on the right side at the beginning, you see that at the beginning you don't have a bell shape, you have a couple of peaks that are actually there, but after 11 weeks you have something which is resembling to one bell-shaped profile, which is there. So this, without any doubt, shows that if you use robotic devices to assist people, you can train the brain, and this is patients doing that on their own. That's not a robotic device. So this is a recovery. Plasticity took over. The problem with this is actually that all of these patients that I mentioned so far, they actually, after 2 weeks, when they stop the rehabilitation, they lose it. So it's there, and why they lose it? Because they don't exercise. So there is this phenomenal wording which says use it or lose it. So as long as they use, as long as they're in training, that's fine. So in order to actually have something that will be there is a threshold. So if you are providing training to someone, you have to bring this person to a threshold. This threshold means get a function. So if you make someone to get a function, then suddenly, with this function, you can provide. If you don't bring someone over the threshold, sooner or later, this person will stop. So if you teach someone to walk, if you make him a walker, and he can ambulate only 3 meters and then needs a chair, this person will lose it. But if you make someone a walker and he starts walking and go to a supermarket, drugstore, other places, then it will be fine. Now, going further, what you can do is you can do this, which is very well known as a constraint-induced therapy, introduced by Taub in USA. And in this technique, you are actually asking a person to maximally use the extremities. And when doing that, you see one of the examples coming from Ina Tarka, from the research in Finland, which we partly did jointly, and partly of that was done, this was specifically done by her own group. So 90% of a day, the person has a splint over a good site. These are stroke patients. So this person is forced to use the paretic arm. That automatically means this can work only in individuals who have some residual function. So if you have someone who is paralyzed and can't do anything, the fact that you brace the good side actually would make him incapable of doing anything. So this technique was demonstrated in many, many experiments that work. And what was done nicely is that it was demonstrated by studies done by magnetic resonance imaging and by TMS, that there are actually major changes taking place within the cortex. The alternative, and that's what I'm talking today, is instead of using the robot, assist the person with electrical stimulation. Assistance of electrical stimulation of upper extremity started for tetraplegic individuals, had nothing to do with recovery, nothing to do with the therapy. Part of that work was started, and the best work was done in Cleveland, Case Western Reserve University by Hunter Peckham and his team, and many, many others. But at the same time, there was a development, an excellent development by Roger Nathan, an Israeli researcher, which was done in Ra'anana. And what he ended up was a device, initially he had in 1974. So he had a system with 14 channels of electrical stimulation, which was controlled by voice and sip and puff. But slowly he moved to a device which was called Handmaster, which is a rather simple device, which is on the market for about $6,000, which provides stability for the wrist based on a plastic splint, and with 3 stimulating channels that are activating the thumb, opening and closing the fingers, and the time machine which opens the hand, closes the hand, and provides the function. So this device was known as Handmaster, then it was taken over by the company Bioness, it's called now SH200, and you saw it here in operation. This device, at least to my eyes, has one major problem, and that's a plastic splint. Because if you have a plastic splint and there is something in the hands, that makes you actually complicates how you manipulate things. So instead of having a splint, another ability is that you actually start using electrical stimulation. And when you start using electrical stimulation, you provide a little more than you would typically have, and that's you have provided stability of wrist by stimulating flexion and extension. And in parallel to that, you provide control of fingers. So with several channels, we built this device for the company Neurodan, now part of the Ottobock. And what you see here is you provide a function to a person. This study included quite a few of stroke individuals. Quite a few is hundreds. And the net effect of that is that actually there is a large therapeutic effect. The therapy is 3 weeks, 30 minutes daily, 5 days a week. And the only thing which people have to do with this is to exercise functional movement. This is to eat something, drink something, comb their hair. And so if you bring them over, when they cross the threshold and they start functionally using their paretic arm, then there is a very good chance that they will continue to use it, if they're motivated. Obviously, if someone is not motivated, then nothing works. Now, this is one of examples, and you see here this was recorded, 18 years ago, in 2000, just around Christmas time. And you see there was no function. 3 weeks later, that's the same person. Obviously, everyone shows some of the best examples, so he is one of the better recovered individuals, and you can hardly discriminate what's a natural recovery compared to the electrical stimulation cost. But since there is a statistical effect of that, and that was done in 230 in total, but in a study that was published in 52 patients, then this means that this is not just that you have few patients in whom that will happen. Now, as I said, electrical stimulation for upper extremity was developed originally for tetraplegic individuals, not stroke. And we did actually a study, and there was joint development with our Prohaska. Well, I was also in Canada, in Edmonton, but they did it with the device, and they came with a device which we called Bionic Glove. There was a multi-center study in quite a few places. There was one paper that came out in '99, where it was demonstrated that individuals who are using that for a long period of time have a nice recovery. These are all chronic tetraplegic individuals. That's a 3 or 4 channel electrical stimulation that stimulates and activates fingers opening, fingers closing, and controlling someone's wrist. This is one of the patients that was in the group who really liked the system and he recovered very nicely. This is a C5 tetraplegic lesion, Asia A. Now, what is important with this is the following. If you look into this not too complicated graph, you see the red bars on the left and right side in both. KIF is the acronym for Quadriplegia Index of Function, a typical scale to measure functioning of a quadriplegic or tetraplegic individuals. The bottom graph is Functional Independent Measure, another scale which is used to measure that. So the score of Functional Independence Measure of 30-some is mostly intellectual functions. So not very much motor function. And if you look into this, into the bottom graph, you see at the beginning of the study, on a day 1, if the system is not turned on, so you don't have a stimulation, the score is about 38 or something like that. But when you turn the stimulation on the same day, you double the score and you come to 70 and you start having some function. If you use this for 6 months, after 6 months the score increases and reaches about 90, which is a level of some or specific functionality. But what is very interesting, if you turn off the stimulation after 6 months, so you take down the system, and that's obviously easy because they're surface electrodes, you end up that the score doesn't really fall down to the beginning. So as a result of 6 months use, chronic use of patients at home and in the clinic, there's an increase in the function in both quadriplegia index function and R. And this is projected here, as you can see. And that was actually the reason because we gave these devices to patients to take them home. And out of 20 patients who were in the program, 18 said, we don't need this. And they didn't want to bother. Positioning electrodes, putting them on the skin, getting to the right position, turning it off, was too complicated to have this little function and the gain. And they gained whatever they wanted. There was another result which came out of that. This is they were asked to do movements in a plane, so to move the hand from one position to the next position, from the start position to target, and 5 times. And there were many targets on the table. And at the beginning, this is 5-minute session, they could do 6 tasks. And after a few months of training, they could do 18 tasks. But what is even more important, at the beginning, you see at the top graph, you see these curves, and the top one is the shoulder angle, and the bottom one is the elbow angle. So this is characterized that you have large excursion in the shoulder and very little in the elbow. But afterwards, you have a synchronized activity of shoulder and elbow, which is typical for healthy individuals. So the recovery of function is there because there is a reorganization in the controller, which starts bringing this to more natural compared to what you have in a difficult study. So this was confirmed in several studies that we did with magnetic resonance imaging and with transcranial magnetic stimulation, where we demonstrated that you have a different silent period, that you have a different, everything changed in that. So chronic electrical stimulation does work very well. What is important with this is the following. That's actually one of the main messages. Electrical stimulation has therapeutic effects. These effects are biggest if it is applied immediately after the onset of injury. So acute use of electrical stimulation is effective. We did a crossover study, and we did this in chronic patients, and without any doubt, the effects are almost neglectable. Once individual develops compensatory strategy, change the strategy, lose some muscles, lose some of the force that can be developed, it's extremely difficult. And short periods of therapies, which are 3 weeks, 4 weeks or so, they actually have very little or almost no effect. Now, obviously, this can be done in a different way for if you don't have and you don't expect therapeutic effects, and I would feel ashamed not to show the best development in electrical stimulation, which was done in Cleveland. So they came with a system which was called Freehand. It was sold in more than 250 copies. There was a company in Europe run by a person who is from Montpellier, actually. This was working for some time, but it turned out that the category of individuals who are actually gaining the function of that is so small that the market is too small. And maintenance of the system and logistics support and everything else turned it down. So basically the company went bankrupt. But the product is still there and it is still being developed because the original idea comes from Hunter Peckham, and Hunter Peckham is still investing his own money into getting a better product. And they made a better product because now everything is implantable, everything is wireless, electrodes are better. So the system in general is working much better than it ever did. And I'm sure that in the future there will be other developments. In the same time, this stimulator can be used for other applications, and one of those I will show you just in a second. Now, the other application of electrical stimulation that I will be talking, and I wouldn't be talking about rowing and bike and other things because there was a deal that we made that I wouldn't talk about that, is restoration of walking. So walking started being restored in Ljubljana many years ago. There are a few individuals, Alois Kralj, still active, somewhat active, in Ljubljana, who was working with spinal cord injuries in walking, and the other one was Franjo Gračanin, whom you can see on the right panel, the right movie, which will start in a second, who was dealing mostly with chronic, with stroke patients. And there was a development, as you can see here, this movie is from 1984, so 35 years ago. And that was actually developed before that. The movie was made in 1984. So there was a system which has 6 channels of stimulation that you can select specific moments when you activate it. There was an open control mode that you select the timing when you wanted, you can select the activity. But the nice development which took place also was the implantable system. And the lady that you will see here had a brain injury, and that's the pattern of her walking because of the brain injury. And she has an implant which is sitting on a peroneal nerve, and she has an implant which is a switch, which is very close to her heel. And so at this point you will see she will, just in a second, now she's turning on the stimulator, which is on the belt here. And when she turns on the stimulator, the stimulator will, in rhythm, trigger and stimulate the peroneal nerve, and you can see the tremendous difference in her gait pattern. Most of research that was done, and there were quite a few devices that are available these days for the drop foot problem, brain injury, and similar things, demonstrated that you can actually do quite a few things with electrical stimulation. You can improve, but the therapeutic effect is relatively low. So the difference between the group that was treated, being on a robotic device like Lokomat or Advanced Gait Trainer or electrical stimulations compared to normal exercise, there's a minor difference. So it's not really proven that you can do that. This is part of a study that was done in Denmark by a group of people that you see here, and I won't go into all the names because of the time. And this was the excellent work with Erika Spike, and I was actually the main person behind that. Now, there are devices that came as that, so that is a functional electrical stimulation that is on the market. Devices that exist is one is from Bioness, the other one coming in from Canada and US studies is Walk8. And Otterwalk took over and basically replicated what others are doing. So there is a switch which comes in the shoe, and there is a stimulator which activates the muscle. There are other developments, some of them done by, for example, Technalia, with multiple electrodes and other. There are things that Christina was working on also, Acevedo here and other. But I don't think that there's actually much of a difference in the performance. So there are other devices. One thing that is getting better and better, and that's actually one of the messages I want to leave with you. One of the main reasons that electrical stimulation is not widespread is that it's not practical sufficiently. If you want to have something on the market, it needs to be practical. If I need more time to put it on than to use it, I wouldn't use it. If I spend most effort to think how to use it and not what I'm doing, I wouldn't use it. And the effort that we're making, and I participated in that for many years, is how we can translate what we understand that we will know into something which is really practical. Because if it starts to be practical, like the mobile phone, then you suddenly start using that. Because if we need 30 minutes to turn on the mobile phone in order to receive one message, we won't use it. But it is unknowing how easy it comes to us, and because of that we use it, all of us. So that's the importance. And with systems like that, that's the problem. So in order to improve the practicality, and I was part of this development, it came out from the work of Andy Hoffer initially, Dick Stein and others in Canada, then Thomas Sinkier from Denmark. The device was built in Morten Haugland, a couple other, and this specific device is an implantable electrical stimulation system, which is activating by a nerve cuff. And this is a device that Otterwalk, because of that, purchased the whole company Neurodan. And right now, as far as I know, is killing the product and deciding not to use it. And the reason for that is that they cannot find surgeons who are actually capable of inserting the electrode in a safe way. So there are complications with the electrodes. There's a problem always, why you want to invest 25,000 euros into an implantable device, if you can do more or less the same for 250 euro with a surface device. So that's an important issue. And I'm not talking against implants, and I'm not criticizing this. Once these implants are perfected, then obviously everyone will go for an implant. You know, going to a dentist, you're looking for an implant, because now they are improved to the point that they work. But before that, you actually didn't want really to use them in an appropriate way. So this can be used as well for walking of people who are quote-unquote injured. And here you see one of the early work coming from Ljubljana by Alois Kralj and Rajko Turk, a physician, a physiatrist who was there. There's a book, Functional Electrical Stimulation, published in 1989, where they describe 112 patients who are walking like that. Some of the events that studied in the country where this was originated actually stopped it because it was used on people who were on the opposite sides in the war. So most of 120 people stopped actually using it because they didn't have technical support, which is really too bad for these individuals, not to mention this situation. So this is one of the patients, a guy from Graz who was using that for about 4 years. Walking to university, he could walk 3 to 4 kilometers with it very slowly. Very supportive family, that's an important issue. Very motivated person, that's the second important, and practical sufficiently so that it really actually made a change in his life. These systems, they need actually to be improved to get a better balance and do other things. And one of the better developments on my side is, I don't think that there is any other system better than what we developed. And this movie is coming from the work that was done in between Miami and Belgrade. And that's the fully automatic control of 6-channel electrical stimulation for walking. And we had patients, 12 out of 12, who could walk up to 1.1 meters per second. They can cover distances that are longer than 1 kilometer. They can do everything they can, but they hated to walk fast. Because when the legs are going fast and they don't know what's happening with their legs, they don't feel safe. So you have something underneath moving fast and you are hanging in the air, you don't know what. So they ended up that they don't want to use this automatic control. So our great effort to make something was perfect, speaking on the automatic control point and everything, but it really didn't make much of a difference for that. In some cases, electrical stimulation need to be combined, and that's a very popular issue these days with robotics. And this is the development, they actually started many years ago, and we had devices like similar to that in the 80s, which we stopped using because of the technology, and that's the movie coming from Cleveland by Rudi Koberic and the group that came out of some of the work from Byron Marsolais. So this is using a freehand stimulator that describes 1 per leg, 8 channels, implants, and using an orthosis on the side. So orthosis, exoskeleton, motorized, is providing stability so that you don't have to stimulate for a long time muscles and you don't have a problem of fatigue. But I wouldn't say that this is really practical. And this needs still a lot of work before it can be improved and brought to something else. Now, there are many others that I should acknowledge, but just want to say that a lot of money was spent in this, and quite a few excellent students of mine, colleagues of mine worked together in various places. In Edmonton, in Canada, where I had a fantastic work together with Dick Steiner, Prochaska, Tessa Gordon, and Andy Hofer. The work that I was doing in Miami at the Miami Project to Cure Paralysis. The work that I was doing in Belgrade, the work that I spent at Center for Sensory Motor Interaction with Tom Sink here in Samara. So a lot of people contributed their knowledge, and I learned a lot because I'm an engineer and I'm trying to learn something in physiology in order to improve that, with an idea to get the smile back on the face of some individuals who are unfortunately handicapped. And that's all what I've prepared for today. Right in time.